article and papers from Dan's group. Or we're thinking about off-resonance imaging. Oh, there are some great experiments from Dan's group. Let's go look at his papers about Faraday and spin-resolved imaging. Oh, we have this idea about spin-orbital coupling. What about that theory paper from Dan's group? So my point in this is that Dan has had quite a broad impact in atomic physics, both cold and atoms and cavities. And I think the highest compliments to him are that we keep referencing his dang works. So, Dan.
Well, thanks, Ian. That's very kind. I return the favor, just so you know. You and all of your colleagues, of course. I mean, we're definitely following in your footsteps as well. And so it's really a pleasure to be here and to talk about some of the work that my group is doing. I guess there's some other topics that I gave apparently an impromptu talk about 10 minutes ago on some of our work, but anyhow, we can just talk about that over lunch or at questions or whatnot. What I'd like to focus on is the work my group is doing broadly in the area, I suppose, of quantum simulation. So you've heard this buzzword quite a bit, but I'll just recount sort of what the idea is. The idea is that, let's say, focus on something like condensed matter physics. There's sort of a natural, I guess now a traditional dialectic that occurs in the study of material science and condensed matter physics. We try to understand the properties of materials in a very general sense. And sometimes that proceeds by finding a speck of material and measuring its properties and then attempting to explain these sort of mysterious properties that we observe. At that point, we hand the problem over to the theorists who then try to boil down sort of a minimal model which they can handle maybe analytically or at least numerically that would explain all of the phenomena. Or sometimes the discovery process starts with the theorists who dream up something rather exciting, but maybe it doesn't have a natural realization yet. And then after figuring out what it might produce in a material, they go ahead and tell the material scientists to try to make this kind of material. A quantum simulator means to sort of intervene in this sort of dialectic. And the idea is that if we have these models of many-body physics, either inspired from materials or meant to inspire new materials, we sometimes have difficulty understanding what these models predict. And we will then turn to like a numerical simulation on a computer to sort of gain some sort of insight and maybe also some exact answers. The quantum simulator is meant to sort of replace or augment that numerical simulation technique. So we'll take a model of condensed matter system, or really now any sort of quantum system, whether it's something that occurs in materials or something that occurs in nuclear matter or something that occurs in dissipative systems in biology or whatnot, and we'll try to create a physical simulation of that theoretical quantum system. So the idea of quantum simulation is to make real representations of simple quantum mechanical models in sort of as clean a representation as possible, and then to study the properties of this physical model to understand what the theoretical model is telling you. The quantum simulation efforts, I guess, that I'll talk about mostly have to do with atoms that are placed in optical lattices. So many of you probably know this already, but if we take several beams of light and intersect them, then we get the periodic pattern of intensity. And that can create a potential landscape for atoms that move within it, which is very similar to the potential landscape that electrons see inside of a material. And the potential landscapes or the periodic structures that my group has focused on have all had sort of a triangular motif. So there's often like a triangular plaquette somewhere within the lattice that we create. And 3 points forming a plaquette already give you sort of a minimal entry into some rather interesting phenomena. So for one, I guess you can just realize that 3 points define a plane. So that means that the physics that comes out in two-dimensional systems, which is often sort of an interesting dimension for physics to explore. It's between where things are described by simple mean field theories and where things sort of don't have enough complexity in them. Sort of right in between sits two dimensions where we get to rather interesting states of matter. So, okay, so the talk will be mostly about two-dimensional lattices. 3 points in a plaquette are also sort of a minimal representation for you, or a minimal construction for you to represent angular momentum. So you can think about eigenstates of systems of a particle that's delocalized in 3 states, and those eigenstates can be circulating. So we hope that working with these sort of triangular plaquette lattices, we'll be able to get into the physics of systems under rotation. And then finally, for things like spin physics, once we have 3 points in a plaquette, we often find that we can create models for magnetism which are beset by frustration, where let's say the spins of that are located on these 3 sites can't agree on a direction to point where they would, let's say, reduce their energy maximally under, let's say, antiferromagnetic interaction. So we hope with our approach to quantum simulation to approach questions that have to do with interesting 2-dimensional physics, systems under rotation, and geometric frustration, both of spin physics and also of orbital physics. So let me introduce one of these triangular motif lattices, this thing called the Kagome lattice. The Kagome lattice comes from a Japanese word which describes this shape of basket. Okay, so there's a Kagome lattice that we have in the lab. And, but we also have one in an ultra-high vacuum chamber, and that one does more interesting stuff. And the way one generates a triangular lattice, a Kagome lattice, is you start with a triangular lattice in 2 dimensions, and you exclude, let's say, every 4th site out of the lattice. So let's say in this lattice, we retain only the blue sites, the sites labeled in blue. In terms of the unit cell structure of the Kagome lattice, let's say we wrapped a unit cell around 4 points of the initial triangular lattice. The Kagome lattice keeps 3 of those sites and excludes the 4th. And the connectivity of the lattice is basically represented again by this basket weave. But you see that it's represented by, it consists of a bunch of triangular plaquettes that all join each other at vertices. And this lattice structure is notoriously beset by geometric frustration. So we can see that, for example, if we have spins that live on the Kagome lattice and they are antiferromagnetically coupled to one another, the energy is minimized when they point in opposite directions. So if my spins are free to move, let's say either on a circle or on a sphere, they will minimize their energy within a single plaquette, let's say by splaying out by 120 degrees with respect to one another. But it turns out that in the Kagome lattice, this particular arrangement of splayed spins does not predict the structure of the entire spin layout in the entire lattice. So for example, even though this plaquette of spins is oriented as shown here, if we look at this plaquette up here, I don't know whether on this site should I place this orientation of the spin or this orientation of the spin. And that ends up leading to a vast, a macroscopic degeneracy of states that all have the same sort of compromised energy for antiferromagnetic interactions. And when you have such a vast degeneracy of states, then other things, maybe subtle effects, will come in and settle the question of overall what is the ground state, what is the low energy state for such a system. So Kagome antiferromagnets have been studied numerically for a very long time. And it's just a hard nut to crack in terms of numerical computations. There's still, as I understand, some debate about which kind of quantum spin liquid state is realized inside of this magnet. There are solid state materials where the Kagome lattice is realized, and people are then trying to study those materials to answer the theoretical question of what the ground state is. So it seemed a natural place for us to introduce an atomic quantum simulator to try to answer some of these questions. It turns out that the geometric frustration of the Kagome lattice also affects orbital physics, by which I mean the motion of particles within the lattice, not just their spins. So to see that, imagine I have a particle that is delocalized on all sites of the lattice, and I ask, what is the highest kinetic energy state for that atom? And that highest kinetic energy state would be one where the phase, the quantum mechanical phase of the probability amplitude for finding an atom at a particular site would be opposite from one site to the neighbor. That would give a state that has maximum kinetic energy. And the task of orienting the atomic, the phase of the wave function to have opposite values at neighboring sites is kind of similar to the task of writing down a spin state where the spin, let's say, would be something that lives in 2 dimensions. and finding an antiferromagnetically coupled spin state in the Kagome lattice. So the result, again, is a vast macroscopic degeneracy of states with the same orbital energy, and that is represented, let's say, in the band structure by the existence of a band that is completely non-dispersing, that includes all of these degenerate states. Or another way of seeing it is that you could imagine writing down a wave function for an atom or an electron that would live at, let's say, these sites around the hexagon of a Kagome lattice, but where the phase of the wave function alternates from site to site. And you see that by destructive interference, this particle can't leave this hexagon. If it wants to escape through this place, you see there's a destructive interference for the paths to reach that site from the neighboring sites that lie within the hexagon. And if I have a localized state, which is a superposition of states with all momentum, that is also stationary, it doesn't evolve, then it means that all those energy eigenstates at all those different momenta have the same energy. So flat bands also mean sort of automatic localization of the atoms. The connectivity, or the idea that spin physics, a frustration in the spin sector, is somehow related also to frustration in the sector of motion, that systems that are spin frustrated are also frustrated for the motion of the atoms, or the idea that that antiferromagnetic spins would arrange themselves in a way that is analogous to particles that are delocalized on a plaquette. And you see the phase of, let's say, this quantum wave function wraps around by 2 pi as I go around this loop. So this connection between rotation of particles and spin physics is an old one. And people for a long time, in trying to understand both the mystery at that time of the quantum Hall states and also what quantum spin liquids represent, have noted this similarity. So studying frustrated spin physics and frustrated orbital physics is connected to both those phenomena. Okay, so here's how we realize these Kagome lattices and other lattices in our laboratory. We take, so we have a gas of rubidium atoms, that's the particles that move within the lattice, and we expose these atoms to a triangular lattice that's formed by beams that come in within a plane from 3 directions at angles of 120 degrees from one another. But we make this optical lattice with light that has 2 different colors, where the ratio of the wavelengths that we use here is actually now exactly 2 to 1. And as I'll show you in a second, we're interested in forming optical lattice or an interference pattern from the intersection of all these green beams. And on top of that, another optical lattice from the intersection of these infrared beams. But we're very interested in the relative position of these 2 optical lattices. And in order to stabilize that relative position against drift and in mirrors and air currents and such on the table, we use some active stabilization at an interferometer, which now is tuned pretty well to where the relative position of the 2 lattices is stable to within about a nanometer. So that means we can create this kind of configuration within the vacuum cell. We can create, let's say, this pattern is produced by the intersection of the 3 green-colored beams in that diagram. So I take 3 beams intersecting at 120 degrees. I make sure the polarization is in plane for this particular situation. Then the intensity pattern of light that's produced inside of the cell looks like this. It has a triangular lattice of locations where the intensity goes to 0. And for the atoms we're working with, the green light acts as a little bit of a repulsive potential. So the atoms end up being localized at the positions where the green light is dark. So that creates a standard triangular lattice in 2 dimensions. And on top of that, we lay another triangular lattice formed by infrared light. And it's positioned so that one of the places where the infrared light intensity is 0 coincides with a place where the green light intensity is 0. And the effect of that is the following. So the red light actually attracts atoms to its higher intensity spots. So if I look at the overall potential that's produced, you see that there used to be 4 sites within a unit cell of the lattice. One of the sites is increased in energy and excluded from the physics of the problem. And the remaining 3 sites, which are labeled here in blue, are equivalent sites, and they form the sites of the Kagome lattice. So you see here 2 of the plaquettes of the Kagome lattice. So we have the ability to produce lattices of one geometry and of another geometry just by turning the intensity of various colors of light on and off. And what can we just do with that ability that is interesting physics in its own right? And that gets me to this topic, which is studying changes in a system that come about from structural changes in a lattice, and also applying, sort of trying out a real task for a quantum simulator, which is testing a theory and seeing whether it's right or wrong. So I'll just remind you that in condensed matter physics, it's very common to find systems where two things occur at once. There's a change in the electronic configuration, or the phase of the electrons inside of the crystal. Some sort of phase transition, maybe between a metal and an insulator or something like that, which occurs simultaneously with a structural change inside of the crystal, where actually the ions within the crystal also change their arrangement. So vanadium dioxide is one very well-known example of it. It's also a very accessible phase transition. And it's one that indeed undergoes a metal to insulator transition, but concomitantly, there's also some kind of structural transition that changes the symmetry of the lattice. And one of the deals with these kinds of transitions in solid-state systems is it can be hard to figure out which transition caused what effect. So was it a structural phase transition, which then changed, let's say, the band structure, which then changed what the electrons do inside of the crystal, which caused the electronic phase transition? Or is it the electronic phase transition, which changed how the electrons are arranged inside of the crystal, which then changes the force which binds the ions, which changes the crystal? So it can be hard to disentangle the two effects in solid-state physics. But in these kinds of atomic quantum simulators, it's actually really easy because we control the structure of the lattice independent from what the atoms inside the lattice are doing. So we can drive a structural phase transition deliberately, and we can see whether it has an effect on the electronic sector, which is to say on the physics of the atoms that are trapped within the lattice. So for us, the electronic, or the phase transition that will occur is not a metal to insulator transition. We're working with rubidium bosons. So for us, the transition is a superfluid to insulator transition. And it's one that occurs in systems that are described by this Hamiltonian, which is the Bose-Hubbard Hamiltonian. It's one where there's particles that hop around in a lattice. So this basically describes band structure. And then the particles within a single site also interact repulsively with one another. And it's now sort of well known within this field that as you increase the strength of interactions, you go from weak interactions to strong interactions, then you transition a system from a superfluid phase where the atoms are delocalized and there's long-range phase coherence within the gas, to an insulator transition where the atoms are localized and where the coherence rapidly shrinks from being having a coherence length as large as the system to finally having a coherence length that's just one or two sites depending on the depth of the lattice. And we know that this, from at least simple theories, we can easily calculate that this transition from the superfluid to the insulating state occurs when at a critical value of this parameter. So U is the interaction energy per site, J is the hopping energy, and this quantity Z tells you how many nearest neighbors a site has within the lattice. So a lattice that is strongly coordinated with many neighbors to a single site would undergo the insulating transition only at stronger interactions, whereas a lattice that is very sparsely connected could undergo the insulating phase transition already when the interactions are relatively weak. And we have a lattice that can transition from one number of nearest neighbors to another. We can either study atoms in this triangular lattice where the coordination number is 6, or in the Kagome lattice where this coordination number is 4. So we expect perhaps some kind of transition to occur simply by changing the coordination number or the connectivity of the lattice. So we see that this is indeed the case. So the standard analysis tool for whether the gas that you've trapped is in the superfluid or the non-superfluid phase is to examine the gas actually in momentum space, not in position space. And in momentum space, that's what these images are showing, if the gas has long-range coherence, then the momentum space distribution shows very sharp interference peaks, kind of like you can see when you're doing interferometry with coherent light beams. So that's, let's say, seen in these pictures. But when the gas is no longer long-range phase coherent and you don't have a superfluid, then these sharp peaks disappear and you get sort of broader, mushy distributions in momentum space. So this is a standard panel of pictures that shows superfluids giving way to Mott insulating states as, in this case, as the lattice is deepened. And for us, deepening the lattice is equivalent to severing the connection between sites and making the on-site interaction more significant compared to the tunneling between sites. But you see already in these images that just qualitatively you can see that the superfluid sort of lives longer. It sort of is retained to stronger or deeper lattice depths. So lattices that have even less tunneling in the triangular lattice than it does in the Kagome lattice. So clearly, just from this picture, you can see that this structural change can drive superfluid gases into the insulating state by severing ties within the lattice. But we'd like to do something more precise than that for two reasons. One is because we're atomic physicists, and atomic physicists should do everything with precision, right? We're supposed to be studying condensed matter physics problems, but with many decimal places. That's, but also we want to sort of establish a practical use of these quantum simulators and really use them to test a particular theoretical question. So the superfluid to Mott insulating transition has been studied also in a quantitative basis in quantum simulation experiments, including some done here. And the focus has been primarily on identifying what is this critical value at which the transition occurs. Basically by methods like I showed you, you look at these images, you try to figure out where the superfluid has given way to the Mott insulator, and then you try to then back out from your knowledge of the lattice what is the value at which this transition occurred. And there's a number of experiments that have been done by a number of interesting methods, and they roughly agree with one another. And the precision of these measurements is at the level of maybe 10 to 20%. So from like the viewpoint of condensed matter physics, like finding a line on a phase diagram to within 10 or 20% is like golden. But from the viewpoint of atomic physicists who are used to measuring in parts per billion, then maybe this is a little bit disappointing. So we'd like to see if we can get more precision in making these measurements. Now, the reason why it's hard to make these measurements with precision is because of some specific features of the quantum simulators, of the experimental systems that we're using. Those experimental systems, first of all, they work with gases that are not, of course, cooled all the way down to zero temperature, where I can predict to you where the transition should occur. Rather, the experiments occur with gases that are at a non-zero temperature. And in fact, the actual temperature of these gases we have trouble characterizing because we just don't have a thermometer that's necessarily quite good in that in these systems. So that adds a complication to how we interpret our data. And a second problem is that the atoms that we're working with are trapped within lattices, and the trapping potential turns out to make the gas also inhomogeneous. The gas trapped in this potential will be dense in the center and dilute at the edges, and a gas that is so inhomogeneous, it would be hard to characterize exactly when and where a phase transition occurred. Phase transitions are always descriptions of systems that are homogeneous and in the thermodynamic limit. And here we have inhomogeneous systems with limited sizes and limited particle number. So we sort of looked around to see if there's a specific aspect of the Bose-Hubbard model that we could answer with a quantum simulator that was beset by these two limitations. And this is what we came up with. Okay, so we can hypothesize a certain scaling relationship in the equation of state, that is the relation between microscopic system parameters and its macroscopic parameters, for systems described by the Bose-Hubbard Hamiltonian like I showed you. And the scaling hypothesis that we'll put forward is something that is suggested by mean field treatments of the Bose-Hubbard system, but they may persist even beyond the mean field limit. So that's what we're testing, whether that's a possibility. In mean field physics, what you end up doing is, instead of trying to calculate exactly the quantum state of atoms that are distributed in a very large lattice, you make an assumption that quantum state factorizes in a way that you only have to figure out the state of atoms at one site, subject to a bunch of neighboring sites that are entirely identical. And then you can basically just assume that that same single site wave function applies to all the particles within the system. It's a It's an assumption that is an entirely local treatment of the Bose-Hubbard system. And being a local treatment, it only pays attention to how many neighboring sites there are in the lattice. It doesn't ask what is the actual geometric layout of the lattice. It doesn't ask us what exactly is the band structure of the lattice. It simply asks how many nearest neighbors does one site have. And as such, we obtain equations of state, so relations between the microscopics and macroscopics of the gas, that are based on the following relation. So the equation of state, which would describe the entire system, would be a specification for what is the density of the system, what is the superfluid density of the system, and what is the entropy per site within the system. So those are the sort of macroscopic observables, the thermodynamic observables, as a function of these microscopic quantities. So if you recall, there were four energies that would enter into the Bose-Hubbard problem. There's the chemical potential, which controls the density within the system. There's the interaction strength. There's temperature, which I hadn't talked about, but that's obviously an energy scale. And then there's also the tunneling energy J. So it won't surprise you that in this equation of state, I can divide all of these three energies by the tunneling energy, because after all, energy has to come in units of something, so that's not surprising. But the specific statement that this mean field theory makes is that you should also divide by the coordination number. That sort of discrete scaling, that's the non-trivial scaling that's in these relations. And this tells you then that any lattice that you describe, any lattice that you look at, really in any dimensions, should all be described by this same equation of state. All you have to do is divide these quantities in the numerators by this denominator, and all lattices will have the same phase diagram precisely. Okay, so this is a local theory, so let's keep with sort of local treatment, and let's take this scaling relation which applies at the single site level and apply it to the entire gas. So now we have to just sort of take an integral over the entire volume that's filled by the atoms inside of our simulator. And in any case, we end up with these scaling relations, that the total number, the total superfluid number, and the total entropy in the system is some scaled function of, again, the chemical potential here at the center of the gas, the interaction strength, and the temperature when all is scaled by Z times J. All right, so now we can test this hypothesis very precisely in the following manner. We take a gas of atoms. The gas of atoms has some number of atoms in it. That's something I can measure very well. It also has some entropy within it, which actually I don't know how to measure very well. But nevertheless, we're going to take this gas and we're going to hope that adiabatically we can place it into one of two different lattices. And if we study the property of the gas inside of this lattice, and we do so at the same value of the scaled interaction strength, then the scaling hypothesis tells you that everything we measure on the two gases must be the same. Because there's three fixed quantities. We have two gases with the same number, with the same total entropy. I don't know what the entropy is, but I know it's the same in the two situations. And the same scaled energy. And that means that in these three equations, I've fixed three quantities, and therefore all the remaining quantities are fixed. That is, these two gases at the same scaled interaction energy must have the same scaled temperature, must have the same scaled chemical potential, and must, for example, have the same condensate number. So that's something we can directly test. So there's the upshot, is from images like I showed you, we count up how much of the atomic distribution is localized in those sharp peaks. That's some sort of measure of the condensate fraction. And we compare it at the same scaled interaction strength in the two different lattice potentials, the triangular lattice or the Kagome lattice. And we find that actually this scaling hypothesis works remarkably well for our system. All the way from a gas that is probably deeply in the superfluid limit to a gas out here that is maybe in the Mott insulating limit, or maybe it's just at high temperature. It doesn't really matter what the temperature of our system is. I don't have to make strong statements about whether this is a Mott insulator or just an incoherent gas. The point is that I've compared two gases at the same entropy. This equation of state should hold everywhere in the phase diagram at all temperatures. So our best fit of the triangular to Kagome data means that we would expect to scale the interaction energy in one case by a factor of 1.5 to match data from one lattice to another. Experimentally, that works out within whatever the 6% error of our experiment. It leaves open the question of why this test worked out so well, because it's clear that mean field theory is terrible for this system, that particularly for a two-dimensional lattice system, mean field theory is awful, but somehow the scaling hypothesis flies through with flying colors. Okay, great. So now let's expand even further the kind of lattices that we can treat in our quantum simulators. And a student, Tom Barter, pointed this out as he was trying to figure out the next experiment to do in the lab, is that simply by rotating the polarization of one of our lattice beams in this configuration, we could produce a rather different kind of Kagome lattice. So now when we rotate the polarization of the infrared light, in particular out of plane, we go from a triangular lattice of 0 intensities to a triangular lattice of maximum intensities. So now the infrared lattice presents a triangular pattern where the potential is deepened. And if we position things right, we can place these bowls in the potential right in between 3 sites of the original triangular lattice. And this new configuration distorts the green lattice in 3 ways. One is, like before, it takes one of the sites within the unit cell and it pushes it up in energy, so it's excluded from our problem. So the remaining sites are Kagome-like in their arrangement, their geometric arrangement. But secondly, this infrared light also creates a little bit of a potential well between 3 sites within one of the plaquettes, let's say the plaquette pointing up, and then also introduces a little bit of a potential hill between the downward pointing plaquette within the Kagome lattice. So it breaks the symmetry that we used to have in the Kagome lattice between, let's say, the up and the down pointing triangular plaquettes. A third thing it also does is it causes the lattice to breathe. So it stretches the sites of the down-pointing plaquette outwards and the sites of the up-pointing plaquettes inwards. So this lattice is also known from condensed matter physics. It's something they call either the trimerized or the breathing Kagome lattice. It was introduced theoretically as a simplification of the Kagome lattice. So since they couldn't figure out what the antiferromagnet in the Kagome lattice does, they instead studied the trimerized Kagome lattice. And it was a very smart thing to do because in the limit of very strong trimerization, this Kagome lattice reduces to a plaquette lattice. So there's basically a plaquette of 3 sites that are strongly coupled. And those strongly coupled sites can be somewhat disconnected from all the other sites. So that means you can start treating this question of macroscopic ordering in this lattice, starting from the microscopic question of what do, let's say, spins do in a single plaquette, and then only afterwards you sort of add a little bit of link from one plaquette to another. There's some weirdly named crystals that also are described by the breathing Kagome lattice. I won't try to pronounce their names. And so anyhow, so we've created them also in an atomic setting. One question was, how do we know we've produced this lattice? What's going to be really our signature? We're looking for a signature that reveals one of the key aspects of this lattice, which is the breaking of spatial inversion symmetry. So that fact that our up-pointing plaquettes are different than our down-pointing plaquettes. So a standard way to look at crystal structure in solid-state physics is to send coherent X-rays through the crystal and look at diffraction. We're going to follow a similar tack. We're going to send coherent matter waves through this lattice to try to see the structure of the underlying lattice. It turned out to be a little subtle to do this. So the first inclination is just to plop a BEC, a superfluid, inside of this lattice, and then allow that superfluid to expand and diffract and show those narrow diffraction spots like I showed you earlier. But it turns out that you don't expect to see a spatial inversion symmetry in those kinds of diffraction experiments, for the reason that the ground state of a superfluid is always a state that has uniform phase all across the lattice, which is to say the superfluid wave function can be thought of as a real function. And real functions, if you recall, have the same amplitude for momentum, or in k-space, have the same amplitude in one direction as they do in the opposite direction. So a diffraction experiment would not directly reveal the spatial inversion asymmetry of the lattice. It wouldn't, for example, allow us to distinguish one trimerization of the lattice where the strongly coupled plaquettes point up from the opposite trimerization of the lattice, where the strongly coupled plaquettes point down. Okay, so we decided to do something different, which is to load atoms inside of this trimerized Kagome lattice, and then just convert the lattice back to this purely infrared lattice, which we do just by switching off the green light. That's very easy for us to do. And now we have a way of imprinting complex phases into the wave function that should reveal the spatial asymmetry of the lattice. So now within this infrared lattice, let's say we have a superfluid with amplitude on these 3 sites of the plaquette. These upward pointing triangles will now rush inwards. The population in them will rush inwards from the potential bowl that's introduced by the infrared lattice. And that produces a pattern of currents within the atomic distribution. And that is something that we can see in momentum space quite clearly. And we can see that this pattern of currents is different in one trimerization of the lattice than another. So this is what the diffraction patterns look like after this sort of perturbation of the lattice. And if you focus in particular on the first order diffraction peaks, you see that the atoms diffracting out of one of these perturbed lattices have a spatial inversion asymmetry. So let's say these 3 sites are largely occupied, which is the opposite of what we get when we start the atoms in the opposite trimerization. So we can dynamically, through this matter, confirm when it is we've produced one trimerized Kagome lattice or a different trimerized Kagome lattice. Okay, now what do atoms do inside of this trimerized Kagome lattice? We wondered whether what effect the trimerization would have, so the distinction between strong and weak bonds, and what influence the spatial asymmetry would have on these strongly correlated atoms. So again, we're going to examine the problem in momentum space. So, and here's how. So imagine, we have our atoms, they're trapped in a lattice, and in the tight binding limit, the atoms in each lattice site are represented by maybe some sort of Gaussian wave function. If we have a system that is deep in the Mott insulating limit, as I told you a number of slides ago, the phase coherence across the lattice is extinguished. And the idea is now that atoms that reside in each neighboring lattice site are completely incoherent with one another. If I examine this position space distribution of atoms, if I examine it in a momentum space, what I see is the following. So one single lattice site diffracts, right? So it expands from position space where it was confined to momentum space, so it expands outwards, right? And we see a momentum space distribution that by necessity spans several reciprocal wave vectors because the atoms are tightly confined within the unit cell. And this same momentum space distribution emerges from each of the sites within the lattice, but because the atoms are totally incoherent from one site to the next, the overall momentum distribution is just the incoherent sum of many of these Gaussians. So they just lie right on top of each other. You see this big Gaussian distribution. Now, in contrast, what happens if you go away from the deep Mott insulating limit to where you have, let's say, just the start of coherence within the lattice, which is to say, just nearest neighbor coherences. All right, so let me focus on what happens if there's a little bit of coherence between 2 neighboring sites in the lattice, characterized by this coherence function being non-zero. Okay, so now I look at the diffraction again, and I look in momentum space. And the atoms in this blue site, they expand like a big Gaussian. The atoms in this green site, they also are Gaussian in momentum space. But now, because the green site is translated from the blue site, the actual momentum space wave function for atoms coming out of the green site acquires a phase factor with respect to that of the blue site. That's simply what translation in position space does for you. So now if there is some coherence from one site to the next, these 2 wave functions will interfere and we'll see a modulation which reflects that interference. So in other words, we will be able to see the signatures of 2-slit interference in the overall distribution of the expanded gas, so long as there's some coherence between 2 neighboring slits. All right, so what will that look like for atoms expanding out of either a trimerized or non-trimerized lattice? Okay, so here's let's say a regular Kagome lattice where what we're going to do is we're going to drive the system into the deep Mott insulating limit by reducing the strength of all of these bonds by the same measure. Or we'll work in the trimerized Kagome lattice and we'll drive the Mott insulating transition by reducing the strength of these weakly coupled bonds, but we'll let the strongly coupled bonds remain strong and at constant strength. All right, So if I look at the diffraction of the atoms in momentum space, and I look along one particular axis, then I will see signatures of nearest neighbor coherences. And in the image, I'll see that, let's say, if I look at the modulation in the image along this direction, I'll see signatures of the coherence between these sites and the coherence between these sites sort of overlaid on one another. All right, so now I think about what happens as we drive into the Mott insulating regime. So we drive up the strength of interactions, or we diminish the strength of tunneling. This nearest neighbor coherence becomes extinguished in the Mott insulating limit. So for the non-trimerized Kagome lattice, I expect both of these terms to asymptotically go to 0, and I expect overall the coherence in my momentum space distribution to go away. In the opposite case, here I expect, again, to suppress coherence along this bond, but along this bond I retain strong tunneling, so I expect coherence to remain on that bond. And therefore, really deep within the Mott insulating limit, I expect some residual coherence to be retained from the bond order inside of each of these plaquettes. And that's exactly what's seen. So we take images like these are the diffraction images, the momentum space images, and we fit them with a function that would extract the nearest neighbor coherence along each of the directions. We average it up along the 3 directions that we observe. So that's what's meant by this nearest neighbor coherence function alpha. So the simple case is, let's say, just the triangular lattice where all the bonds are the same. And if we drive the triangular lattice through the Mott insulating transition, then lo and behold, we see coherence washing away completely as we go into the deep Mott insulating limit. The images here, they still show some sort of 6-fold modulation, which is the signature of coherence, but by the time we get to this point, even that little bit of coherence is extinguished. In contrast, in the trimerized Kagome lattice, even when we're deep within the Mott insulating regime, even long after long-range coherence has been totally killed in the system, we still see a great deal of nearest neighbor coherence in the system, which we expect because we've retained these strong bonds. There's a second aspect of these images that we're only now realizing, we should have realized a while ago, but that the breathing, the displacement of sites in the Kagome lattice is also, in the trimerized Kagome lattice, is also visible in these images. And actually, we have to correct some of our data from this slide upwards because of that effect. OK, but the persistence of nearest neighbor coherence in this lattice doesn't really tell us everything, because we were trying to develop the story that the coherence exists on one of the bonds of the lattice, but not the other bond of the lattice. So how do we distinguish the signature from one of these bonds from the other one of those bonds? And the way we do so is by applying phase shifts. So now we're going to take these coherence functions, which are strictly real in the ground state, and we're going to make them complex functions. We're going to do so by changing the energy of one of the sites within the triangular plaquette, which we can do just by switching off one of the lattice beams transiently. And the effect of that, let me look specifically at the case of the trimerized Kagome lattice. The effect is the following. So we're deep in the Mott insulating limit, so this term is gone. That's our prediction. And all the coherence that we see is from these strong bonds. But these strong bonds are going to turn out to give a 2-slit interference pattern that shifts in space as we change the phase of the coherence. So it's like taking a 2-slit pattern in optics and putting a little bit of a phase shift on one of the slits. You'll see that your optical interference pattern shifts sideways when you do so. So we're looking for a signature of that shifting sideways, and that would indicate that it's just one of these 2-slit interferences that's visible in our data. If at the same time we had also picked up a strong signal from coherence on the other bond, that would have produced an interference pattern that equivalently slides in the other direction. And if they were of equal strength, then the displacements would cancel. So this is what the momentum space images look like after this sort of transient imprinting of a phase. And you see this strong evolution of the momentum space distribution, which basically signifies exactly this picture, that all of the coherence seems to be on a single site and not on a single bond and not on the neighboring bond as well. Okay, so here's sort of more quantitatively how these coherence functions evolve after our transient imprinting of the phase. And I'll just say that in these data, we see signatures of some many-body physics. That's a dephasing that occurs due to interaction. And we also see some glitches that come about from the breathing of the lattice. We actually now see the transient motion of atoms after the lattice is switched. But these images are these data are basically revealing the picture, the basic picture that I was emphasizing, that in the deep Mott insulating limit within this trimerized Kagome lattice, nearest neighbor coherence persists deep into the Mott insulating regime, and it's asymmetric. It has the same spatial asymmetry of the lattice itself.
Where are alpha and beta?
Yeah, so that's fitting the data to a cosine plus sine modulation. That extracts the real and complex phase of actually a difference between the two neighboring sites. So the fact that these modulations have roughly the same amplitude, it's a little troubling that one has a larger amplitude than the other, but that's an artifact. But the fact that they have basically equal amplitude is telling us that all the coherence is on one site. Yeah. Whereas here, more in the superfluid regime, you see the sine function has low amplitude. So that tells us that we're picking up also coherence from the weak bond as well as the strong bond in those cases. Okay, so we'd like to further expand what quantum simulators can do. And that leads to a new experiment that my group is now setting up, which is to tame a new set of atoms and to bring more elements from the periodic table into the ultra-cold regime. And our motivation to do so is roughly based on the following slide, which people here will recognize. So in condensed matter physics, one is rather interested in creating topological superfluids. So these are systems where you get Cooper pairing between electrons, but the electrons live in a particular band structure, which is subject to strong spin-orbit coupling. That allows for for a particular Cooper pairing between electrons that leads to the superfluids that they form having a certain topological character. The topology manifests itself, as often does in topological physics, by things that occur distinctly at the edges of these kinds of superconductors. Either, let's say, the two ends of a one-dimensional superconducting wire, or let's say the vortex within a two-dimensional superfluid. And these edge modes and these vortex modes are, presumably they are Majorana fermion excitations where there's a particular symmetry guaranteed by the topology of the superfluid wave function that pulls a fermionic state to zero energy and makes particles and holes equivalent. And a prescription for producing topological superfluidity in condensed matter is to find a material that has strong spin-orbit coupling and then to make it superconducting. And the way it's suggested, let's say by Jay and others, is to take some material that has internal strong spin-orbit coupling but doesn't naturally have superconductivity and stick it on top of a superconductor, and it'll sort of acquire superconductivity by proximity to its neighbor, and the end result will be the realization of Majorana fermions. Okay, so all the ingredients to do this exist also in a cold atom setting as they do in a condensed matter setting. Like in solid-state physics, we have fermions to work with. We need particles that will interact with each other so that they'll undergo Cooper pairing. So we know how to create interactions. We need spin-orbit coupling. So you guys know, Ian and colleagues know how to produce spin-orbit coupling in gases by subjecting them to transitions under laser light. And then finally, we need to have the equivalent of electron spin. So we need two or more spin states of these fermions to live in this spin-orbit coupled material. The problem is, at present, it's hard to find one system that shows all of these features at once. Okay, so find a system that has fermions, that has stable states of fermions, and that also has long-lived spin-orbit coupling, which is what you'd want in order to create these topological superfluids. So here's the periodic table, and here are the elements that have been brought to quantum degeneracy so far. And examining this table, you see they sort of divide into two camps. So the alkali metals, the alkaline earth atoms, and then a few of sort of the closed shell atoms that have also been laser cooled, they all have the property that in their electronic ground state, they have zero angular momentum. And what that means is that as far as the interaction between light and between the atom and light is concerned, the interaction is essentially isotropic, right? Light doesn't have a way of sort of tugging on the atom and rotating its angular momentum in sort of an easy manner. One can create spin-orbit coupling through anisotropic light-atom interactions, where the polarization of light and the spin state of the atom both have to be factored in figuring out how strong the light-atom interaction is. We can realize that for these closed shell atoms, but only by going very, very close to atomic transitions where we can gain some of the spin-orbit coupling of the excited states. So it's for that reason, in particular, the fermions that we have, let's say lithium and potassium, they turn out to have really weak spin-orbit coupling in the excited state, so it's really hard to create long-lived spin-orbit coupling in these gases. Alternately, we have these lanthanide atoms that have also been made quantum degenerate, and they are very anisotropic. They have a ton of angular momentum in the ground state, so no problem creating strong spin-orbit coupling, even for light that is very far from the atomic resonance. Unfortunately, these atoms are also very strongly magnetic, and the strong magnetism of these atoms makes it so that you can't have mixtures of different spin states that live for a long period of time. There's a dipolar relaxation that kills those mixtures. So it makes you wonder whether there's something else we should be looking at. So we looked around the periodic table through the NIST spectral databases, and we looked for elements which had a variety of isotopes, where the laser cooling is not ridiculous, where there's non-zero angular momentum in the ground state, but not so much that the atom is also very strongly magnetic. And we came up with the following, that we believe that the atoms in the titanium group and the iron group actually are quite amenable to laser cooling. And we've started an experiment to laser cool titanium atoms in particular. I'll tell you a little bit about that. And on deeper thought, we've also figured out that all these other atoms are also laser coolable by the same idea. So now there's maybe a dozen or so elements that people have not really worked with yet that I think all can be efficiently laser cooled with reasonable laser light in wavelength ranges between about 550 and 350 or so. And at least the laser cooling stage of producing ultra-cold gases, I think, is manageable for all these atoms. And so we're focusing at first on titanium. So titanium is a rather stable nucleus, so it has lots of isotopes, both bosons and fermions. In its ground state, titanium has 4 valence electrons, 2 of them in the d orbital and 2 of them in the s orbital. So it's got a submerged d shell. It's a complicated atom. Its collisions will be really interesting to figure out. Paul will figure them out for us. Okay, so in its ground, so for titanium, this is the ground state. 2 electrons in the d orbital, 2 electrons in the s orbital. So the spectrum of titanium coming out of that ground state, for many of the transitions, is kind of like the spectrum of calcium. If you regard this as being a core that's untouched by the laser light, which is not always true, and you're just thinking about driving transitions for these 4 s electrons. So maybe you realize that calcium has been laser cooled, so titanium can be laser cooled as well. But it turns out calcium is really unappealing or unsuccessful for laser cooling, because after you've driven atoms from the 4s to the 4p level, there's often a decay in calcium into the 3d shell, and that leaves calcium in sort of a metastable state, and you have to sort of pump it out of those states so that you don't lose the atom. For us, so that would occur in this case as well, so I wouldn't recommend laser cooling out of these ground states. This pumping into the d orbital, though, can work in our favor. So titanium also contains a lot of metastable states with this other low energy configuration, where one of the s electrons moves into the d orbital. Remember that the s and d orbitals are fairly equivalent for the transition metals. And in particular, if we look at the metastable state where these core electrons and also this s electron are all spin polarized, then we're in a fortunate situation that the spectrum out of this state is almost like the spectrum of potassium now. It's as if we have just a single valence electron, this 4s electron, which you can drive in a 4s to 4p transition, and decay downward has to respect all the spin that's stored inside of this system, so it will always come back to the same starting point. So in particular, this A5, F5 level is a great state for laser cooling. It has a laser cooling transition at 498 nanometers, which was that teal colored laser light that I showed you on the previous slide. Very beautiful. And the line width is 10 megahertz. It basically looks like an alkali atom. It should be good for polarization gradient cooling. It should be just a standard a standard transition to work with. Titanium also happens to have another transition, which is not universal to all the other transition metals, but it has another transition at 1040 that's like 10 kilohertz wide. So it should also have a very narrow laser cooling possibility as well. So we're working on this in the lab. Of course, we have to figure out how to get atoms into this metastable state. They're populated there thermally. That's what we'll start with. But then we'll have to pump them later.
So have you considered that if two metastable atoms collide, they can actually exit out in the ground state?
I've considered it, but I have no idea what to say about it. So it could be like metastable helium, where sort of the spin polarization of the system kind of protects it from those decays, or it could be not. It could actually, the atoms they have these anisotropic d orbitals, and so you would expect that collisions between them can sort of affect the atom strongly, so we'll have to see. So it may be that we can laser cool the atoms in this level, but then we have to put them down into the ground state to, let's say, do things like evaporative cooling. So that's as much as we've considered it. But for now, we want to see a little blue-green Mott. I've run out of time. I wanted to raise a discussion in this crowd about what we should be doing with cold atoms in space. So cold atoms are up in space. This is a totally separate topic. There's cold atoms up in space, and they're having some problems with their rubidium spectroscopy, but basically they're able to make rubidium BECs flying overhead every 90 minutes. So look up, you'll see a BEC. And people are starting to do sort of experiments on them, how slowly you can get them to expand under free fall and such. And there's a follow-on mission that's being planned as a collaboration between the German Space Agency and the American Space Agency. And in order to guide the construction of this cold atom lab, NASA has appointed something they call the Science Definition Team, whose job is to guess what any user in the next number of years might want to use this facility for, and then based on those best guesses to make sure that the facility is outfitted for those kinds of projects. So this experiment will be a user facility that people in the US and Germany can basically submit a proposal and they can run experiments on this thing that's floating out in space. So we try to imagine all the things that our entire community of proposers might want to do up on that space craft, and make sure that it's equipped to do all those experiments. So what we've proposed that the instrument be designed around is a set of sort of 6 topics that range from doing work to study atom interferometry with very long propagation times because the atoms don't fall out of your vacuum chamber. Experiments on coherent atom optics where you make like matter waves that basically, they don't fall, they just propagate straight, and you can study atom optics in a sort of a textbook configuration. New configurations for both scalar and spinor Bose gases, and in particular ones that make use of the ability to trap atoms in optical potentials inside of a box potential, and more. So if people want to talk to me about that at lunch, I'd be happy to get your input because there's still a chance to make sure that, some new widget is added to this apparatus. Okay, so with that I will finally finish. So the work on the optical lattices was done by the people highlighted in yellow. Tom Barter's just moved on to Microsoft. Masayuki moved off also into industry, Zephy, and then an undergraduate student, Alan. The work on titanium has been launched by a postdoc, Kaylee, now joined by Scott and a few undergraduates. I did not tell you about our atom and cavity experiments. I didn't tell you about lithium-rubidium molecules and gas mixtures. But I will tell you that if you want to come work with us, in particular as a postdoc, just send me an email. Thanks.
So in the Kagome lattice experiment, if I understand this correctly, you have a huge spin. So
yes.
Do you have plans?
Do we have plans to?
Yeah.
Yes. So for we're working right now with rubidium bosons. The natural, let's say due to exchange interactions or superexchange, the natural spin-spin interaction you would get in that case would be ferromagnetic. That's not terribly interesting in the Kagome lattice. So you really want to get to the antiferromagnetic situation. So what we are hoping, let's say, with the rubidium bosons is either to study orbital physics once we stick atoms in. Remember that flat band is at the top of the band structure, so we can think about ways to get atoms at the top of the band structure. Maybe even then to do spin physics while the atoms are at the top of the band structure, which I think would make the interactions antiferromagnetic. But we're also realizing that rubidium is probably not the right atom for a lot of these experiments. So in short order, I'm hoping we'll add potassium in there. We've already built the lasers. And with potassium, we'd be able to work with both the Feshbach-tunable boson and the Feshbach-tunable fermion. And in particular, working with the fermion, I think will open up finally the really rich physics that the Kagome and also the trimerized Kagome lattices should have.
You talked about scaling. I was wondering if you could also see finite size scaling with B-field exponents or something like that. You have, I guess, a lot of control over the size of your optical lattices, and there ought to be a shift.
I don't have plans to do that, but that is something you would ask of a quantum simulator, isn't it? You would ask to really test that finite size scaling, and we can imagine either circumscribing like a box around our lattice to limit its geometric size, or maybe constructing the lattice in a more programmable way so that you could have a plaquette and then two plaquettes and sort of build up the size of it, and look at system parameters. And one thing that would work to your advantage in that regard is that we do have hundreds of thousands of atoms to work with. So even for the very small size lattices, we can just make very many copies of it all at once and obtain all the information we want out of a single measurement. So that's an interesting line to investigate. We are interested in, particular in the this is different from what you're saying, but in the trimerized Kagome lattice, we do have this knob where we can go from very much like the disconnected plaquette limit to the connected plaquette limit. And to do at least the few body physics, do the exact quantum state spectroscopy of n particles in m sites with or without spin, that's something we should have access to, which I think overlaps also with a task in quantum computing, where people talk about the quantum variational approaches to studying quantum systems. Anyhow, so we have some ideas along those lines, but not a specific one for how to do the scaling.
Do you see any critical exponents?
In our experiments, we have not looked closely to try to measure critical exponents. There are, elsewhere in the literature, people are looking, I guess primarily the critical exponents that people have seen is in dynamics experiments. Cold atom experiments, they have some real difficulties in studying equilibrium at large scales, right? We're always arguing about whether the system is actually at equilibrium, and we have trouble with the size of the system and the fact that it's inhomogeneous. The real strong suit of these atomic systems is the fact that we can drive them really with high control out of the ground state into non-equilibrium situations. So the most rigorous scaling work I've seen has been on dynamics as you sweep across phase transitions.
Okay, one more question. Okay, Jake.
So did you compare the scaling, this mean field thing for the Kagome versus the square lattice? I mean, you don't have a square lattice, but everyone else has a square lattice. What's the equal score?
Yes, no, I did not look at those. I wouldn't know how to compare one experiment to the other because I don't know what entropy those experiments were done at. If you look through the papers carefully, like that's either a hidden statement, like we make a BEC as cold as we can and then we do something, or there's like a rough, ballpark estimate of the entropy. So to take, an experiment in one location, experiment in another location and compare them is somewhat difficult. On the other hand, within a single setup to just adiabatically, again, I'm putting that in air quotes, adiabatically transition to one lattice versus another, that seems straightforward. We did think about the possibility of comparing a Kagome lattice with connected planes, which would have z equals 6, to the triangular lattice in 2 dimensions, right? I mean, there we should see like a really striking difference, but we just didn't get around to it.
All right, let's thank Dan again.